A complex number has real pairs and imaginary pairs. When it comes to a complex number, one way we can check whether a given number is real or imaginary is by taking the conjugate of that number. Let's look at the problem statement first. Let u and v be complex numbers such that the magnitude of u and the magnitude of v both equal to 1, and u not equal to v and u not equal to negative v. So we have to show that the given number 4uv over u plus v whole squared is real. So we have to prove that this number is real. On the other hand, we also have to show that this number, u plus v over u minus v, this is imaginary. So in order for us to be able to show that, we can recall one of the properties of complex numbers that we discussed in one of the previous lectures. So let me remind you over here briefly. So the idea here is that if we have a complex number z, and if I take the conjugate of that number, if that produces z itself, the positive z, and that will happen if and only if z is real. Z is real. So if and only if is really a two-way statement, which means if this part is true, then this must be true. On the other hand, if this is true, this must also be true. So that's for the real part. For the imaginary part, if z is a complex number, you take the conjugate of z, and if it produces negative z, that will happen if and only if z is imaginary. Z is imaginary. If z is imaginary, then this event will occur. On the other hand, if this event occurs, then z is imaginary. That's the essence of if and only if statement. So we're going to make use of this idea. Let me box this off. Now let's go ahead and try to prove the first part of the problem, where we are given a number and we have to show that this is real. So for the ease of working out, let's assume this number to be equal to z. So z is equal to 4uv divided by u plus v whole squared. Now we would like to prove that this is real. And to prove that this is real, we just have to take the conjugate of that number. And if it turns out that it produces the number itself, then the number z is real. Let me write down how we're going to do that. So to show z is real, it suffices to show that z is equal to the conjugate of z. Okay, so the first thing to do here is to take the conjugate of z. So let's go ahead and take the conjugate of z. So what is z? Z over here is 4uv divided by u plus v whole squared. And we are going to take the conjugate of the whole quotient over here. So the conjugate of this quotient is then going to be the conjugate of the numerator and the conjugate of the denominator separately. That's according to one of the properties of complex number. Now from here, the conjugate of this constant term produces the same constant term, and the conjugate of u and v we can write according to the properties of complex numbers. We can write the conjugate of u times the conjugate of v. Similarly, using the properties of complex number, we can write conjugate of u plus conjugate of v whole squared. Now at this point, I don't know what conjugate of u and conjugate of v, what these things are. Let's go back to the problem and see if we have any information about the conjugate of u and conjugate of v. We don't have any direct information about the conjugate of u and conjugate of v, but we can see the magnitude of u and magnitude of v, and it's a good idea to work with the magnitude square instead of magnitude, because if we use the magnitude square, then we can use one of the properties that says the magnitude square of a complex number, let's say z, is equal to z times the conjugate of z. So in this case, the magnitude square of u, it can be written as u times the conjugate of u. So from there, we might be able to derive something. So in this part, since we don't know what u and v's are, what I want to do is I want to find out what u and v are. So we figured that u times the conjugate of u is equal to the magnitude of u squared. But in our problem, it was given that the magnitude of u is equal to 1. So we can use this property now. We can write u times the conjugate of u 1 squared, right? So from here, I can write the conjugate of u is then going to be 1 over u, right? Similarly, on this part, what I can do, we know that in our problem it was given the magnitude of v is also equal to 1. So from here, if you want to use the square of the magnitude of v, then we can actually use one of the useful properties. So v times the conjugate of v. So from here, we can see that v times v squared, and the square of the magnitude of v is basically 1 squared. Then it gives you conjugate of v is going to be equal to 1 over v. These things will be super useful for our problem. So I'm going to box this off over here because we might be able to use it over and over again. So let's go back where we left off. So this is where we were. So we're going to go back to that statement. So this was basically z bar, right? So then z bar is going to be equal to 4 times the conjugate of u, and we know now that conjugate of u is 1 over u and conjugate of v is 1 over v. So I can use these from this box, and we're going to write divided by 1 over u plus 1 over v whole squared. Great. So now let's go ahead and work it out a little bit. Now we can break this thing down. We can break down the denominator. The numerator stays the same. So in the denominator, we can write 1 over u whole squared plus 2 times 1 over u, 1 over v plus 1 over v whole squared. This is by the a plus b formula, a plus b whole squared formula. Now at this point, let me remember what was the goal for calculating the conjugate of z. The goal here was really simple. We wanted to show that the conjugate of z is equal to z, but in my case, z is 4uv. It doesn't have any term that looks like 1 over u, 1 over v, something like that. In our current position, we have a bunch of 1 over u and 1 over v. We need to get rid of all of them. Then we're going to get a term that looks like 4uv, which means we can reach closer to our goal. Since we're multiplying by this term, we're going to have to divide by the same term. So let's do this and work it out a little more. And it turns out that on the numerator we get 4uv, and on the denominator what we're getting is u squared and u squared cancel each other out. If we multiply this through, then we're going to left with v squared over here. Similarly, we're going to be left with 2uv plus u squared. Okay, so from here what I can write is 4uv, and this term will be u plus v whole squared. But hey, isn't this the term we started off with? And this is the term which we assume to be z. If you recall that z was 4uv divided by u plus v whole squared, and this is exactly the term we ended up with. So this is z. So we were calculating the conjugate of z, and we found out that the conjugate of z is the z itself. Therefore, I can claim that the number z that I started off with is real. That is what we wanted to check. So I'm going to write, therefore, as I assumed the number as z, and the number was 4uv divided by u plus v whole squared. So this number is real. And that is exactly what we wanted to show. Now for the second part of the problem, we are given another number, and we would like to prove that this number is an imaginary number. Now let's assume that this number is equal to w. And how to prove that this number w is imaginary is if we show that the conjugate of that number w is going to be equal to the negate. And the way we can show that the number w is imaginary is if we take the conjugate of that number w, if it spits out a negative sign. So then we can infer that my number is imaginary. So let's go ahead and work it out. Now, second part of the problem, now let w is equal to u plus v divided by u minus v. Now, according to our understanding of the properties of complex number, we're going to write to show that w is imaginary, it suffices to show that the conjugate of w spits out a negative sign, so it becomes negative w. So without further ado, let's just calculate the conjugate of w. So the conjugate of w, this is my w here, right? So the w is u plus v divided by u minus v. I'm going to take the conjugate of this whole quotient. Now, following the properties of complex number, I can write this as the conjugate of the numerator and the conjugate of the denominator. Also, if we follow the properties of complex number, we can also write this numerator as the conjugate of u plus conjugate of v. Similarly, I can write conjugate of u minus the conjugate of v. Previously, we didn't know what the conjugate of u and conjugate of v is. In the middle of the first calculation, we found the conjugate of u and conjugate of v to be 1 over u and 1 over v. So we're going to make use of that in this part of the problem. So I can write the conjugate of u as 1 over u plus the conjugate of v is 1 over v. Similarly, in the denominator, I can write 1 over u minus 1 over v. But our goal is to show that the conjugate of w is equal to negative w. But I have to reach w first. And if you remember the w, in w there were no term involving 1 over u, 1 over v. So we need to get rid of these quotient terms from here. So in order to do that, what we can do is we can multiply this term with u and v. Then you see u and u will cancel each other out, and we're going to be left with v over here and u over here. So you multiply and divide by the same term. So you multiply it through, then what we're going to get is v plus u divided by v minus u. So from here, if I factor out negative 1 from the denominator, what I'm going to get is u minus v, and at the numerator, I can write this as u plus v. And this looks like w, but we have a negative here, so it's going to be negative u plus v divided by u minus v, which is essentially w. This is what we assume w to be, so this is negative w. So we started off with calculating the conjugate of w, and we found that it spits out a negative sign and it results negative w. And that satisfies the condition for checking whether a given number in the complex domain is imaginary. And we can see that this is purely an imaginary number because its conjugate is negative, the number itself. So therefore, we can write the number w, which we assume to be u plus v divided by u minus v. This number w is imaginary. Okay, so that was a rather easy problem. We started off with the idea that if we take the conjugate of a complex number, and if it turns out that this is just the complex number itself, then the number is real, and if it spits out a negative sign and the number itself, then this is imaginary. Based on that idea, we assumed the number, given number, to be equal to z, and then we take the conjugate of that, and then using some of the properties that we derived from the given information on the question, we find that this is exactly the number itself after taking the conjugate of it. So the first number is real, and this is what we wanted to prove for the first case. For the second case, we assume the number to be w, and we take the conjugate of that, and it turns out that it spits out a negative sign and the number itself. So this is an imaginary number, so everything checks. Great. See you in the next lecture.